Before the video begins, just want to mention that I have written a text version of this whole tutorial, and you can check that in the link in the description. Basically, it will cover the whole solution and the intuition, same as what I will be covering in the next 10 or so minutes. You can refer to that when you need to, and that's it. Hey everyone, today let's try to solve another LeetCode problem. So today's problem is called minimum absolute difference between elements with constraint. So basically in this problem you are given an integer array nums and an integer x, and you are required to find the minimum absolute difference of two elements in the array such that they are at least x indexes apart. So in other words, we have to find a pair I and j such that the index difference of I and j is greater or equal to x, and also their values is minimized. So let's take a look at the first example. In this first example, you are given numbers 4, 3, 2, 4, and x equals 0. We can just pick 4 and 4 because the first 4 have an index of 0 and the second 4 has an index of 3. So 3 minus 0 is 3. So the absolute difference of the index is 3, which is larger or equals to 2. That's why we are able to do it. And having 4, 4 is 0, which is the lowest we can get. So that's why we can just return it as the answer. For the second example, the given array is 5, 3, 2, 10, 15. And x is equal 1, and we should return 1. Basically, you can iterate all pairs, and you will find 3, 2 is having the lowest that we can get. And also, the index of 3 is 1, and the index of 2 is 2. 1 minus 2 absolute is 1, which is greater or equals to x. That's why we can use this 3 and 2. So let's say that x is not 1, is 2, then we cannot use this 3, 2. So then the answer, I think the answer will probably be like 5 and 2. So that's basically all of the problem description. And let's think about how to solve it. So let's take a look at the first example again. Because we are only interested in the index of each value, so it might be beneficial for us to keep track of all the indexes of each value. Basically, I will try to create a dictionary where the key will be the value and the value will be an array of indexes that it has appeared in nums. So for 4, it appeared in 0 index and 3 index, so I just write 0 and 3. And for 3, it appears at index 1, and for 2, it appears index 2. That's it. We have 4, 3, 2, and we have the x is equal to. So first obvious thing to check is that we just go through every value. If the smallest index minus the biggest index is greater or equal to x, in this case, 0 minus 3 absolute is 3, and then it's greater or equals to 2. That's why we just can directly return 0 if that is the case, because we cannot do better than 0. But what if there is another case? How about we make x equals 1 to make things more interesting? So if we compare this to leftmost and the rightmost, we cannot get the answer immediately. So we have to pair it with others. But what should we pair first? Obviously, we should pair with 3 first. And if we can pair with 3 with any of these things, then we don't care about 2. Because if 4 can pair with 3, then we will have an answer of 1. So even if we can pair with 2 somehow, we don't care that, because pairing with 3 is better. That's why we always want to go from sorting order. In this case, I will just go from the smallest to the biggest. I will visit 2 first, and then 3, and then 4. So let's say, first I'm going to check if 2 can be paired with itself. If it can, then I just directly return 0. And if it cannot, then I should mark down something in case the future element will want to match with me somehow. So now I change x equals 1 now. Let's see how can we reach the answer. So when you reach 3, and what options do we have? Well, we can either treat this 3 as the left, or I can treat this 3 as the right. By right or by left, I mean the left of the pair or the right of the pair. The left of the pair means the smallest index of the pair. The right of the pair is the larger index of the pair. So let's assume that we only have one index now, but we're going to assume we have more. So let's say it's 4, 5, 6, 7, 8. So if I'm going to assume this 3 to be left of the pair, then which index should I pick to make it most likely to fulfill x? So the answer is, if I'm treating this 3 as the left, then I might as well just choose the leftmost one, because there will be something in here or something in here or something in here. Then if I choose here, then this distance will be shorter. And if I choose here, this distance will be shorter. And it's always the best to choose the leftmost possible. That's why when I'm assuming 3 is the left of the pair, then I'm going to choose the leftmost one. Similar thing, if I'm treating 3 as the right of the pair, I'm going to choose the rightmost one. But let's say that I treat 3 as the left of the pair and I choose this one. Which index should I pick? Well, that's why we have to keep track of the rightmost of the previous one. Because let's assume again, we have something like 10, 15, 17, 20. We have a lot of indexes here. And if I'm trying to assume 3 as the left of the pair, then I don't want to pair it with something like 10 or 15 or 2, right? It's more beneficial to pair with the largest possible. Similar, if I'm assuming 3 as the right of the pair, I don't want to pair it with 10 and 15. I want to pair it with 2 because it will have a larger x. That's why every time we're going to keep track of the leftmost and the rightmost of each seen value. But that's not the end of the story. It is possible that none of these will fulfill the requirement of x, so we have to go even lower. But let's think about it. If I'm treating the later element, such as 4, as the right of the element, now if I am reaching 3, 3 is a smaller value. I mean, the gap of 3 will be smaller comparing to the gap between 2 and 4. And also, if there is more value in here, so 3 will always be having smaller gap than 2. And also, now 3 is having a smaller index of 2. So even if we compare the smallest index, we will see that we have no reason to pair 2 or use 2 as the left pair of the index, right? Because I might as well just use 3, because 3 have an even smaller index than 2 here, and it have higher chance to fulfilling x. Moreover, 3 is having a smaller gap than 2 when I compare it to others values later, because we are visiting in a sorting order. So what I'm trying to say is that we should maintain a monotonic stack for the leftmost and a monotonic stack for rightmost index. And then we can perform a binary search after having this stack, because a monotonic stack is sorted in order. So that's why we can perform a binary search to see what is the closest value that fulfills the X requirement. That's pretty much all for the overview. Okay, first we're gonna initialize n as the size of the array, and I'm gonna create the dictionary for recording the indexes for each value, and then we're just going to fill in the dictionary here. And then at first, in the worst case scenario, we're just going to randomly choose the difference between the last one and the first one just as the first answer. And we're going to create an increasing monostack and a decreasing monostack. And then now we're going to iterate every values in the nums in a sorting order. So we're going to get the leftmost one and the rightmost one of all the indexes. So if the rightmost one and the leftmost one is already greater than x for their index difference, we just return 0 because this value can match with itself. Otherwise, we're going to try to match for L for this particular element. So we're going to check for the decreasing stack using binary search, and then we're just going to get the middle of the range. So if this current mid is fulfilling the X requirement, then we will just update our answer if it is also smaller than our current global best answer. Then we go greedy because we want to get closer to current indexed. That's why we set low equals to mid plus 1. Otherwise, it means that this X requirement doesn't work. We have to go lower in terms of the boundary. Then we're going to match for all. We do the similar thing, but this time we're checking for the increasing stack instead of the decreasing stack. And again, we're just going to check for the middle one. And if this middle one is fulfilling the X requirement, then we're going to update the answer if it is also smaller than our global answer. Otherwise, if it is fulfilling, then we just also set low equals to mid plus 1 because we want to go greedy and get as close as possible to our current index. Otherwise, we have to go further away from our current index to try to search for an answer. And then now we're going to fill the monotonic stack for the decreasing. So in this stack, we will just keep decreasing, as we mentioned, because when we go to a larger index, this decreasing stack will always be used to pair with the L. That's why this decreasing will be a potential allo for the next pair. So that's why we will use allo to store in this decreasing stack. And also, if allo is even greater than the previous decreasing stack, then it doesn't make sense to keep the previous one, right? Because this allo is even greater than the previous one, and then it will have smaller gap comparing to whatever is on the stack, because we are reasoning from the sorted order. That's why we can just discard them. And finally, just append it. So the first element we're going to append is just the index, because we have to use it in here later to decide whether to discard it or not. And the second element is going to be the value, because we have to use it to calculate the value difference later in line 31, for example, and line 21 as well. So that's for the decreasing stack. And for the increasing stack, we're going to do the similar thing, but this time this will be an increasing monotonic stack. So after doing all of this, and we'll just return the answer, because we just keep updating the possible answer here. And when we finish all the searching, this answer will be the minimum possible. That's why we can just return it on line 43. And that's pretty much all for all the code implementation. Let us try to submit that. Okay, accepted. So the time complexity for this will be O n log n. Basically, this comes from the sorting here, and also the binary search we do here also is n log n. And for the space complexity will be O(n), basically coming from this index of value, and also the increasing and decreasing stack, potentially reaching the size of n2. So that's pretty much all, and I hope you have learned something, and I will see you next time. Bye bye.